Hi, and welcome back to the fifth and final video in this second lecture on Covidenomics. In this video, we're going to be using the concept of a payoff matrix. Now, you've probably come across that in your introductory economics course. However, if you haven't, just have a look at the YouTube channel there, which also has all of these videos. And if you look at video 16 from the first year microeconomics course, it will give you a bit more details on payoff matrices and the idea of dominant strategies. We're going to be looking at a slightly different approach to game theory here, and we'll talk more about game theory during this course. Just a reminder of where we're up to. Remember that this beta, this reproduction number, is a key parameter in our SIR epidemiological model to track the progress of a virus. And it has two parts. The first part is E, the exposure rate, and the second part is this P, the probability that if you're exposed, you get infected. And where we got to last time is that we looked in more detail at this E and noticed that unlike the regular assumption in the SIR model, the exposure rate will actually be determined by people's choices, by how much social interaction they choose to undertake. And we showed that both in theory and from the evidence, this level of social activity, so therefore this E, will alter over the course of a pandemic. In this video, we're going to go a bit further. We're going to show that not only is E endogenous, but there may not be just one simple, easy to solve outcome for the level of social interaction and therefore the level of E. We're going to look at situations where there are multiple alternative outcomes that can exist in society, what economists call multiple equilibria. To see this, I'm going to start off in the situation before the pandemic. What I've got here is called a payoff matrix. It involves two players. We've got player A and player B. And each player has two alternative actions they can undertake. They can either socialise or they can not socialise. And so the four boxes that we have here are just going to show the payoffs or the returns to each player depending on the sets of actions that both players undertake. So notice here that the payoff to player A is going to depend on what player B does, and the payoff to player B is going to depend on what player A does. Now, where are each of the payoffs? So the payoff to player A is simply going to be these top right-hand payoffs, the ones that I've highlighted in green. While the payoffs to player B, they're these bottom left payoffs, the ones that I've now highlighted in yellow. So how do we read this payoff matrix? Well, let's suppose player A chooses to socialise and player B also chooses to socialise. Then they're going to be in this top left-hand box here, and the payoff to player B is going to be 20 and the payoff to player A is going to be 20. But now suppose that player B chooses not to socialise, but player A still chooses to socialise. Then player A, well, we're going to be in this left-hand column still where A socialises, but we're now going to be in the bottom row because B chooses not to socialise. B gets a payoff of 0 and A gets a payoff of 1 now. The way I've drawn it here, it's symmetric, so if B chooses to socialise and A chooses not to socialise, well now A gets a payoff of 0 and B gets a payoff of 1, just sort of the mirror image of that box down here. And finally, if they both choose not to socialise, well, we're in the right-hand column because A is not socialising, we're in the bottom row because B isn't socialising, and so they both get a payoff of 0. What we're capturing in this payoff matrix is a pretty simple idea. If everybody goes out and socialises and there's no pandemic, then there's a lot of buzz, they go off to a bar, there's people all around, and they have a good time, so they get a high payoff each. But what are the alternatives? Well, if people decide not to socialise, stay at home, watch a bit of television, not nearly as much fun, but they also affect other people because when player A, for example, goes out to the bar, player B is home watching the television, the bar's not buzzing, it's not as much fun. So the payoff to player A goes down when they socialise but B doesn't. Of course, they could both stay at home watching television, and that would give them each payoff of 0. So what's the actual game we're playing here? Well, let's assume that player A and player B are going to make their decisions. They're going to make them independently. They can't coordinate with each other. So what we have here is sometimes called a simultaneous move game. In general, in these games, what one player is going to do depends on what they think the other player is going to do. Now, in this particular game, it's pretty trivial because there's dominant strategies. But let's just run through the logic. It'll matter in the next version of the game. So let's start off by looking at player B. And let's assume that player B thinks that player A is going to socialise. So what we've done is we've literally eliminated this right-hand column. Player B thinks that the relevant payoffs will be in the left-hand column, where player A chooses to socialise. Well, player B faces a pretty simple decision. If player B socialises, A is socialising, so B will get 20. If player B chooses not to socialise, whilst A is socialising, they'll get a payoff of 0. So pretty clearly in this situation, player B is going to want to choose to socialise because they predict that they will get a payoff of 20. And it's pretty easy to see that if we turn our attention to player A, and player A believes that player B will choose to socialise, then player A will also want to socialise because they get a payoff of 20 rather than 0. So here, the situation where both player A and player B socialise is what we call a Nash equilibrium. Given that I believe B is going to socialise, if I'm player A, I want to socialise. And given that I socialise, player B wants to socialise. It's self-reinforcing. They're simultaneously consistent actions or strategies. Let's just check that there aren't any other Nash equilibria of this game. To see that, let's assume that player B thinks that player A is going to choose not to socialise. What will player B want to do? Well, if player B chooses to socialise, they get a payoff of 1. If player B also chooses to stay at home and not socialise, they get a payoff of 0. So in this situation, player B is going to choose to socialise, even if they believe that player A is going to choose not to socialise, because they get a payoff of 1 rather than 0. But why can't that be an equilibrium, where A chooses not to socialise and B chooses to socialise? Well, because A will now want to change their behaviour. Notice that if player A believes that player B is going to socialise, we're in the top row, then player A is also going to want to socialise because they get a payoff of 20 rather than 0. So that box can't be an equilibrium. We end up back with socialise, socialise. So in this situation, socialise, socialise is what we call a unique Nash equilibrium. The outcome that we predict pre-pandemic is that everyone goes out to the bar. Here I've rewritten the payoff matrix for a situation during the pandemic, particularly when the pandemic is in early stages. Now I haven't changed the actions. The players can still choose either to socialise or not to socialise, but I have changed the payoff. Whilst you still get a nice payoff if you go out to the bar and the bar's buzzing, it's now risky. You don't get 20 anymore, you only get 10, because there's that risk of going out to that buzzing bar, you're going to pick up COVID-19 and die. Similarly, I've changed the payoffs if both players choose not to socialise. Now they both stay in their homes, they're both watching their televisions, they may be doing a Zoom call with each other, but they're safe from the pandemic. They're free from that uncertainty, that fear of getting infected with the virus. So it's a lot better outcome to stay at home when the other person's staying at home. So we've given them payoffs of 12 each in that situation. But what happens if one chooses not to socialise and the other does socialise? Well, the one that does socialise now goes along to a bar, risks getting infected from the bartender, from the bar staff, the place isn't buzzing, it's not much fun. So they get a payoff of -2. The one who stays at home, well, they're not getting as much fun from staying at home. They sort of, my mate's gone off to the bar, maybe I should have gone to the bar. They get a payoff of 8. And again, it's going to be symmetric. So if B doesn't socialise, they get 8 when A chooses to socialise, but A gets -2. So what's our predicted outcome now? It's slightly more complex. Let's assume that player B thinks that player A is still going to go out to the bar. So player A is going to socialise. So from player B's perspective, we're playing in the left-hand column. So let's just get rid of this right-hand column. Well, player B is now going to be choosing between either also go to the bar and get a payoff of 10, or don't socialise, stay at home and only get a payoff of 8. So with these payoffs, in this situation, player B, if they think player A is going to be socialising down at the bar, player B would prefer to socialise and also go to the bar. And of course, because it's symmetric, the same holds for player A. So one outcome, or what's called a Nash equilibrium here, is going to be that both players socialise. If each player thinks the other player is going to the bar, they want to go to the bar too. And that's self-reinforcing. And so one outcome is both players socialise, both players go to the bar. But what happens if player B thinks that player A is not going to socialise? Well, in that situation, we're going to be in the right-hand column, so we can get rid of this left-hand column from player B's perspective. They think that player A is not going to socialise. So what's player B's choice? Well, player B could choose to socialise. They could go to the bar. Bar's not going to be buzzing. They're risking infection. Bad situation. Or player B could also choose to stay at home. They think A is going to stay at home. If they stay at home, yeah, it's not great like being in a buzzing bar, but at least they don't risk infection. So they'll get a payoff of 12. 12's bigger than -2. So if player B believes that player A is going to not go to the bar, that they're going to stay at home, then player B will also choose to not socialise. And again, that's symmetric in this situation. The same holds if player A thinks that player B is staying at home. So we've got another equilibrium here. We've got another self-sustaining Nash equilibrium where both players choose to not socialise. If I think you're not socialising, I prefer not to socialise, and vice versa. So we have 2 predicted outcomes now during the pandemic. We have 2 Nash equilibria. One where everybody continues to socialise, and the other where everybody stays at home. And you'll notice that I've done these payoffs so that from a social perspective, we're actually all better off if we stay at home. We get a payoff of 12 each, but that may not be the outcome. We may end up socialising because we think everybody else is going to socialise, even though that will end up with a worse outcome for everybody. These sorts of games are sometimes called coordination games because you're in a situation where all people playing the game want to coordinate on doing the same thing, in this case, either all socialising or all staying at home, not ending up in the off-diagonals. However, it's got important policy implications in a pandemic because it can mean that even though the pandemic breaks out, and even though you think everybody should be staying at home, everyone may still go out and socialise because they think everyone else is going to socialise, even though that could be a bad thing for society. We see examples of that in the current pandemic. So think about face masks. So rather than socialise, don't socialise, think about wear a face mask, don't wear a face mask. Well, you're much happier often wearing a face mask if everybody else is wearing a face mask. You're happier not wearing a face mask if everybody else isn't wearing a face mask. Socially, we probably want everybody wearing a face mask. But you've had situations which have been shown in different states in the US. Some states, face mask wearing is common, and people sometimes get abused if they're not wearing a mask. In other states, you've seen face mask wearing being uncommon, being viewed as giving in, And people get abused if they do wear a face mask. So you get this outcome where very few people wear face masks. So when we're thinking about this endogenous response to the pandemic, we can end up with very different outcomes for society just simply because of social norms. So we get to the seventh lesson when we put economics on top of our SIR model, and that is that there may be multiple potential outcomes or multiple equilibria, which means that otherwise similar societies may have very different outcomes in the face of a pandemic. So just let's summarise where we've got to in the last two videos. Firstly, we saw that people will endogenously change behaviour in the face of the pandemic, and that will lead to a lower level of social interaction, just simply because of the risks of the pandemic. But in this video, we've seen that the story may be more complex, that there's a coordination problem that may exist in society with regards to social interaction, with regards to other health policies such as wearing face masks, and that we may get outcomes that are suboptimal for society in the sense that, for example, everyone continues engaging in social activity because everyone else is, even though we would all be better off calming down, staying at home for a while. One reaction to the importance of these endogenous changes in behaviour is that, well, maybe the government doesn't need to do anything. In other words, when the pandemic breaks out, people will automatically change their behaviour to reduce the risk of infection, and maybe that's enough to prevent the pandemic from spreading, to lead to a socially optimal level of pandemic control. That would be nice. Unfortunately, the same economic theory tells us that's not going to be enough. There are two basic reasons why we'll need further government intervention. The first is that we've got a whole bunch of negative externalities going on. So if I go out and engage in social activity, sure, I risk getting sick myself, but I also risk getting sick and passing on that infection to other people. Now, if I'm just considering my own welfare and not the welfare of the other people, I'm going to engage in too much social activity. So even though I might cut back to limit my own risk, I'm still creating too much risk for other people. So in that sense, you want government to further restrict social activity. The second reason is the coordination problem. As we saw, even if everyone would be better off by restricting activity, that doesn't necessarily mean that it will automatically occur when one person's decision depends on what other people are doing. And in that situation, we may need the government to come along and say, well, sorry, you will be staying at home because that's going to be the rule. Or, guess what, guys? Even though it's not normal for you to wear a face mask, you've all got to be wearing a face mask. So creating a new social norm through the government policy. So now we come to our eighth and final lesson from this second lecture, and that is that the pandemic will cause a reduction in economic activity regardless of government policy. This is possibly our most important lesson, because what it means is that once we've got a pandemic, we're not talking about a simple trade-off between a bit of economic activity and a bit more health care. No, the pandemic will change the economy. As people change their behaviour, stop going to restaurants, to bars, avoiding supermarkets and so on, that's going to cause dislocation in our economy. It's going to cause a drop in economic activity. It's going to cause unemployment. It's going to cause, as it did around the world with COVID-19, a recession. So we've now got a situation where the pandemic has changed our production possibilities. And the only way we can get economic activity back up again is going to be by dealing with the health issues. So we're not talking about a trade-off between economics and health in a pandemic. We're talking about a situation where the two have to move together. To get economic recovery, we need to solve the health problem of the pandemic. In his book on the economics in the age of COVID-19, Joshua Gans thinks of this as the pandemic taking a bite out of our production possibilities frontier. It's as if our frontier has had a section of it removed because of the pandemic. And instead of the usual nice trade-off around our production possibilities frontier, we're talking of a situation where we now have to move both the economy and the health system together. That it's not one or the other. They're now complements to each other. Understanding this lesson and the endogenous nature of changes in economic activity is really important when you see headlines such as this in articles and for public policy commentators who say we can't afford the lockdown, economic costs are too high. No, what they're forgetting is that the economic cost is due to the pandemic. It will be there. Yes, lockdown may have a marginal effect, but we've got to ask, not is the full economic cost a result of lockdown, but is it worth the extra, the marginal economic cost to try and get the health benefits and get the economy started again? But you also want to be wary of headlines like this, views that suggest that, well, once we reduce and remove the lockdown, the economy will just bounce back. What they're forgetting is that the lockdown doesn't cause the recession. The lockdown may worsen the recession, but if you simply remove the lockdown without the pandemic being brought under control, then people aren't going to resume their pre-pandemic lives. They're going to be worried about infection, risk, and potentially death. And so the economy's not going to bounce back if you remove the lockdown too early. All that you're going to do is extend the economic problem. We've done a lot in this second lecture, so let's just summarise. We started off with the basic susceptible, infected, recovered model to predict the pattern of a pandemic. We noticed that while the early part of a pandemic may involve exponential growth in the number of infections, that growth rate starts to decline naturally as more people are recovered, the chance of passing on the infection decreases, we reach your herd immunity threshold, and the infection starts to die out. However, there were a lot of limitations with the basic SIR model. We noticed that it could be extended in a whole variety of ways, but even then, applying this in practice has a problem, and it's the basic government information problem. At the beginning of a pandemic, the government doesn't know a whole lot of things that it needs to know for the SIR model. It's not going to know the basic reproduction number. It's not going to know how likely people are to be infected if they're exposed to the virus. It's not going to know how long it takes to recover. What's the likelihood of recovering or dying? How many people will need critical or intensive care in hospital? All of those are unknowns that the government has to work out while the pandemic is in progress, because it's the progress of the pandemic that provides the government with the information it needs. However, even then, the basic SIR model is limited because it ignores changes in human behaviour, and there will be significant changes in behaviour due to the fact that there is a pandemic. We saw two particular sorts, the individual change and the coordinated change. And what do they mean? Well, they mean that the pandemic will follow a very, very different path. Because of these changes, a different path to that predicted by the SIR model, and that similar societies, because of a coordination problem, similar societies may also have very different paths for the pandemic. And there's two ongoing reasons why we need government policy. And that is that even when people reduce their social interaction, there are negative externalities, and there is the underlying coordination problem. But sometimes people don't coordinate on the right outcome from society, although they're individually doing the best thing by themselves. And finally, we looked at the issue of fixing the economy. We noticed that these endogenous changes in behaviour have strong economic consequences, and on some predictions, 90% of a reduction in economic activity due to the pandemic is not due to government policy, it's endogenous. It's people changing their behaviour. This has a strong implication for government policy because it means that fixing the economy and fixing the pandemic are really two sides of the same coin. It also means that we shouldn't be saying, well, the cost of a lockdown is a reduction in economic activity. No, the cost of a lockdown is the extra reduction in economic activity on top of what will occur anyway, possibly only an extra 10%. And secondly, we've got to be really wary about saying, well, let's just get rid of a lockdown and the economy will bounce back. Because again, the lockdown's only 10% of the problem. The other 90% potentially is due to the fact that people are scared and they change their behaviour. And if we don't remember that, we will simply design the wrong policies. I've mentioned a range of references as we've gone through, particularly this last video in this set. But there's a couple more here that you might want to read. They're available online. This is one that I referred to earlier on, Avery et al. It looks at the SIR model and discusses its limitations and some extensions. And here's a nice piece from the conversation, just looking at exponential growth. That's all for now. In the next lecture set, we're going to start looking at actual government policies and how the government should think about those policies and the end game for the pandemic. Talk to you then.